there's a cable stretched across two telephone poles here, and we know the tension and the string density. We know that the wind is blowing across here, creating a vibration, which has 5.5 wavelengths in there. We know the temperature is 20 degrees, and at that temperature, the speed of the sound is 343 meters per second. We're trying to figure out what the wavelength of the sound and the frequency of the sound is that's being produced at this from this particular vibration. So in order to do that, we need to figure out this. Since we know the tension and the linear density in the string, then we can easily calculate the velocity, because that's just going to be the square root of 450 divided by 0.02 kilograms over the meters thing. So now we have the velocity of this string here, and because of that, we should be able to calculate the frequency, and the frequency is going to be the same for the string and for the sound over here. So let's try to calculate that. We need the wavelength. In order to calculate the wavelength, let's just get it from there. We're going to need to take 26 and divide that by 5.5. So let's say 26 divided by 5.5. We get 52 over 11. What is that? So 52 over 11 is the wavelength here. So let's try to get that frequency real quick. That would be this whole thing here, 450 over 0.02, and then we're going to divide that by 52 over 11. So that gives us the frequency. Frequency is 825 over 26. So now that we have the frequency, this frequency is again going to be the same here. So yeah, that's going to be 825 over 26. And now we can figure out the wavelength, because we have 343, and we just divide that by the frequency. And so we can get the wavelength is 10.81.